Okay, so we already seen memory mapping. Now we are looking at IO mapping, input output mapping. So there are two types of mapping in here. One is peripheral mapping. Peripheral mapping is where we are going to put input output devices. They are going to have 8-bit address, and we are going to interface or map them. Second is going to be memory mapping. See, in both these cases, we are going to connect input output devices only. We are not going to connect memory, but there are two ways of connecting input output devices. One is to give their particular address, their 8-bit address to the microprocessor. Other way is to give their 16-bit address, just like memory. They will be treated like memory locations. This is going to be 16-bit mapping. So see what happens in peripheral mapping is, we are going to connect devices like keyboard, computer, monitor, whatever you are going to connect, and we are going to have 8-bit addresses. They are going to have 8-bit addresses. So maximum number of devices that can be connected. See, since address of each device that is to be connected is 8 bits long, so number of devices, maximum number of devices that can be connected is 2 to the power 8 or 256. This is a limitation. With peripheral mapping, that only maximum number of devices that can be connected is only 256. So in peripheral mapping, each memory location is going to have a 8-bit long address, and suppose you have connected a keyboard and the address for keyboard is AE. If you input AE at the accumulator and use instructions like in and out, you can input the data from keyboard. So we are using the instructions in and out in peripheral mapping. In IO mapping, we are using the instructions in and out. So basically we are using instructions like in AE. What happens is, any data can be input from the device connected at location AE, at address AE. Suppose we have connected a keyboard at this location AE, so whatever you are giving, whatever data you input through the keyboard, that will come inside the microprocessor. Then you suppose you perform some operation on it, add B. Then we are giving the instruction out CF, and we have connected a display screen at CF. So what happens is, we are taking the input data from the keyboard, we add the contents of register B to this data, and then we are displaying it, we output it at CF, the screen connected at CF. So this is how, using instructions like in, out, we can input or output the data from any devices connected to the peripheral. Each device is going to have a 8-bit long address. Okay. Next we are going to look at memory mapping. Okay, one more pin that we saw. We have seen a pin named as IO/M bar. Okay, so when we looked at the architecture, when we looked at pin diagram of 8085, we saw this pin IO/M bar. This pin allows us to select which peripheral is connected. If we have connected some input output device IO, then the status of this pin is going to be 1. If this pin is 1, IO is selected. If this pin is 0, memory is selected. Memory is active low, IO is active high. So if this pin is 1, IO is selected, input output devices are connected, then this will be 8-bit peripheral mapping, and if this is 0, memory is selected. Okay, so if I make this pin 1 and read bar or write bar as 0, then I can read or write from the input output devices that are connected. If I make this pin 0 and read bar or write bar 0, then I can read or write from the memory. So using these pins, you can read or write from input output devices or from memory. In peripheral mapping, in input interfacing an IO device, in peripheral mapping, we are going to make this IO pin as 1. If we are using memory mapping, that is if we are locating the devices as memory locations. If we are giving them 16-bit addresses, then I am going to make this pin 0. Then we are going to treat them as memory locations and read write from them. But in that case, we cannot use this in and out instructions. This in and out instructions are going to work only for 8-bit addresses. Okay, if you are connecting devices using this peripheral mapping, if their devices are having 8-bit long addresses, only then we can use these instructions in and out. In case we are using this memory mapping, in case of memory mapping, see what happens in memory mapping. First thing is number of devices that can be connected increases. Since now the maximum number of devices that can be connected, it becomes 2 to the power 16, okay, which is much larger than this number. But the problem is size of memory decreases, okay, size of available memory decreases, because what you are doing is you are treating some devices as memory locations only. So the available size of memory, see, we can look at an example. Suppose you have connected a device, you've connected a keyboard, say you've connected a keyboard at location 2FFH. Now you cannot use the same address in the memory also, so addressable memory, usable memory decreases. So this is an advantage with memory mapping, although number of devices that can be connected increases. Then we do not use instructions like in and out. The instructions that we are using here are STA some address, STA address, or LDA address. What do these instructions do? This instruction is going to store the data of the accumulator at the desired address, and this is going to load the accumulator with the data at this address. The operation is same, okay. This instruction is going working like out instruction. This is working like in instruction. So the function is same, but the instructions changes. Here you can get, here we can have 16-bit address. So with the memory mapping, memory interfacing, you are going to use this instructions. Okay. So here status of IO/M bar is going to be 1, and here IO/M bar is going to be 0, because we are treating devices like memory locations here. Okay, and also when we saw the pin diagram for 8085, we saw that there were 2 status pins, right? We have seen 2 status pins, S1 and S0. So we are just going to quickly look what is the function of those pins. Suppose this is IO/M bar pins, this is S1 and this is S0. If IO/M bar is, suppose IO/M bar is 1, okay, first let us assume it as 0. Then if S1 and S0 are 1, 1, 0, 0, 1, okay, we are considering three cases. See, S1, S0 both cannot be 0, right? Since IO/M bar is 0, that means functions are taking place from memory, okay, we are going to access the memory. Now when S1 and S0 both are 1, we are having opcode fetch. This is opcode fetch cycle. When this is 0, that is we are accessing the memory, but S1, S0 are 1, 0. This stands for memory read, and 0, 1 is memory write. This is memory write. Fine. So this is what it stands for. This is what status of pins, status of this S1 and S0 signify. If IO/M bar is 1, that means we are working with the input-output devices. Now similarly, when this is 1, 1, 1, 0, 0, 1. When this is 1, 1, what happens is, we see IO/M bar is 1, that means we are working with the input-output devices. When both of these are 1, this means INT A bar, interrupt acknowledgement, is being sent. Okay, 1, 0 means input-output read, 0, 1 is input-output write. Fine. So this is what interfacing is. This is how you interface a memory output device, input device. And if in any case you are going to write a ALP to input some data from a input output device, output some data, you are going to use two instructions, in and out. And in case it is a memory mapping, then you are going to use STA and LDA. Okay.